Okay, in this lecture we're going to continue looking at some topics from geology. First, we're going to talk about seismic waves. Those are the kinds of acoustic waves that get generated by earthquakes, for example. And we're going to see what seismic waves reveal about the Earth's internal layers. We're going to talk about the theory of continental drift and the theory of plate tectonics. And we'll look at some evidence for plate tectonics as well. So first of all, what are seismic waves? So seismic waves are a kind of an acoustic or sound wave which travels through the earth. And so when rock under the earth's surface moves or breaks, energy travels in the form of these seismic waves or these sound waves which cause the ground to shake and vibrate. This is what we commonly call an earthquake. And what's really cool is that by analyzing these seismic waves, we've been able to get a very detailed view of what the Earth's interior is like. Now, that may not seem like a very big deal, but it actually is a really big deal. And here's why. The Earth is actually a really big place, at least compared to us. I mean, we're tiny in comparison to the size of the Earth. And we can't actually drill down very deep into the Earth. And so there's really no other way for us to know how our world is built. What does the world look like on the inside? The way that we know what we know is because of these seismic waves that have traveled through the earth and interacted with the interior. And based on how those sound waves have changed, we can determine about the makeup of what is going on underneath. And so we'll talk about this a little bit more, but that's the basic idea. We have sound waves traveling through the entire surface of the earth into the interior of the earth, and by studying how these waves are affected by the earth, we can deduce things about the structure of the earth itself. Now, here's a picture showing our basic understanding of the different layers of the earth. And so the earth is surrounded by a sort of a thin skin. Think of it like the rind around an orange. It's this relatively thin skin that covers the entire surface of the earth. And we call that outermost layer the Earth's crust. And the crust's width is anywhere from 10 to about 60 kilometers. Now, underneath the Earth's crust is a region that we call the mantle. And the mantle extends down much deeper into the earth. And then below the mantle is the Earth's core. And the Earth's core has two parts. It has an outer core and an inner core. Now, we're going to talk about each of these different regions separately, but this is the broad picture. This is the big, bird's eye view map of the Earth's structure. Now, how do we know what we know? As I mentioned earlier, we know a lot by deducing things from the different types of acoustic waves that travel through and around the earth. Now, there's two different broad classes of acoustic waves that we talk about in this context. The first is body waves, and these are waves that travel through the Earth's interior. Now, in addition to that, there are things called surface waves, and these are waves that, as the name implies, only travel around the Earth's surface. Now, each of these has two subtypes. One of them is called P waves, and the other one is called S waves. P stands for pressure, and S stands for shear, and we're going to talk about the differences between the two, but you can also think of them as primary waves and secondary waves. The primary wave travels faster, and so if there's, for example, an earthquake, it's going to send out both the P waves and the S waves. The P waves are going to arrive quicker because those waves move faster. In addition to the P waves and the S waves, which again, these are body waves. These are the waves that travel through the Earth's interior. There are also a couple of different types of surface waves, specifically Rayleigh waves and Love waves. So we want to talk first about P waves, which our textbook mainly calls them primary waves, so that's what I'll call them just to be consistent. So primary waves are longitudinal acoustic waves. What does that mean, longitudinal? Well, to understand that, you have to understand that waves are generated by vibration. If I have something that is vibrating back and forth, it can generate waves. Now, longitudinal waves are waves that get sent out in the direction of the vibration. So this guy's vibrating back and forth this way, and it's going to be sending out waves in the same direction of the thing that's vibrating. That's what we call a longitudinal type wave. And they basically compress and expand the material in which they move. So you can imagine as this guy moves over, so I've got something that's vibrating, it's generating waves, and so as it moves over here, as it vibrates this way, it causes stuff to bunch up and compress over there. Whereas on this side, it gets stretched out. And so this guy moves this way, it bunches stuff up over here, and it stretches stuff out over there. Then when it vibrates the other way, it gets reversed. So it gets bunched up over here and stretched out over there. And so these waves, they get pushed in these directions where you have regions where the material is bunched up and regions where it's stretched out. So to recap the key points, these primary waves, they compress and expand the material through which they move, and this compression expansion occurs parallel to the wave's direction of travel. In other words, the wave travels out in the same way that the thing is vibrating back and forth. Now, another very, very important characteristic of primary waves, these longitudinal waves, is that they will travel through any type of material, solid, liquid, or gas. So solid things like rock, liquids like magma or water, even a gas like air. Primary waves can travel through any type of material. And as I said previously, they're also the fastest. And so they travel the fastest. The next kind of wave that we're going to talk about is the secondary waves. And these waves are transverse waves. In a transverse wave, the vibrating thing that is creating the wave vibrates at a right angle to the direction that the wave is moving. And so imagine, for example, you had a rope that was tied to a wall. So I've got a rope here, and it's tied to a wall over here. And if I took one end of the rope and I shook it up and down, what will happen is that you'll get a wave traveling towards the wall. So if I shake it up and down one time, I'll get something like a pulse that's traveling. On the other hand, if I continually shake it up and down, I'll get a wave like that that's traveling towards the wall. The part that's shaking is moving up and down, but the wave is traveling at a right angle to that motion. And so that is an example of a transverse type of a wave. And so we can see that secondary waves are transverse, and in regards to seismic wave, they're going to vibrate the rock in an up and down or side-to-side motion, and the transverse motion occurs perpendicular to the wave's direction of travel. So if the wave is moving this way, the thing that's vibrating back and forth is going to be moving at a right angle to that. Secondary waves will travel through solids, but here's the key thing. They are unable to move through liquids or gases. And so this is going to be really, really important to understand. And of course, we said previously that P waves are faster. That means the S waves, the secondary waves, are slower. So they'll get there last. Now, next we can talk about the other broad category of waves, surface waves. And surface waves, they're the slowest of all the seismic waves, and that means that they're going to be the ones that are last to register on a seismograph. In other words, I have an earthquake over here, and the sound waves travel through the earth, and I have a detector, in my city over here. The P waves are going to get there first, and then the S waves, and then the surface waves. And so, the different speeds determine which ones are going to get there first. Now, one type of surface wave is called a Rayleigh wave, and Rayleigh waves have kind of a rolling type of a motion. They roll over and over in sort of a tumbling kind of motion, similar to the way that the ocean moves. This tumbling motion occurs backwards compared to the wave's direction of travel. And this, as the wave travels through the earth, through the surface of the earth, it causes the ground to move up and down. Now, another kind of surface wave is a love wave, and that has similar motion to the S waves. There's a horizontal surface motion that is side to side, and this sort of whip-like side-to-side motion occurs perpendicular to the wave's direction of travel. So let's check our understanding. The most destructive earthquakes are caused by the passage of surface waves. Why is that? A, they travel faster than the other seismic waves. B, they occur in the crust, the densest layer of the earth. C, they occur at the surface where the ground shakes up and down and from side to side. Or D, they travel deep into the Earth's interior. Well, we know it's not going to be D because surface waves don't travel into the interior, they travel on the surface. And we know they don't travel faster, they're actually the slowest. Now, it is true, they do occur in the crust, which is the outermost layer, but the crust is not actually the densest layer of the Earth. So that leaves C. They occur at the surface where the ground shakes up and down from side to side. And that is actually our answer, C. And so think about this. Surface waves are traveling on the surface. Where are all of our buildings? Where do we live? We live on the surface of the planet. So that's the thing that's being vibrated by the earthquake caused by the surface waves. So that's why they're the most destructive. If we had some sort of deep underground dwelling, miles and miles below the surface of the earth, then a different kind of wave might be more destructive. But for us, it's going to be the surface waves. Now, I said earlier that sound waves reveal a lot of things about the structure of the interior of the earth. How is that possible? Well, it's because when a sound wave travels through different types of material, its speed changes. In some materials, the sound will move very quickly. In other materials, the sound will move more slowly. And so as the sound velocity changes when it goes from layer to layer of material, we can actually measure in a lab what the velocity of sound is in different materials, and we can figure out, in this part of the earth, the sound's moving this fast, so it must be made out of this kind of material. And not only that, we can say, okay, this layer is this deep, and so on. So we can reveal a lot of things about the interior structure of the earth just by measuring the sound passing through it. Now, in 1906, Richard Oldham observed that P waves and S waves travel together for some distance, and then they encounter a boundary where the S waves stop and the P waves refract. That means they bend. Now, this refraction, this bending, that's how we know that the velocity has changed. Because when you have a wave traveling from one medium to another medium at a different velocity, the direction of the sound wave changes. In other words, the sound wave will bend. It'll change direction. And so this is one of the ways that we can tell that the sound is passed from one material into another material. But what's really interesting about this, so let's think about what's going on here. We have an earthquake, for example. That earthquake is generating both P waves and S waves. But then, after they travel some distance, the S waves stop. Now, that's a big clue about what's going on, because what do we know about S waves? They can only travel in solid materials. They cannot travel through a liquid. But P waves can travel through either solids or liquids. And so that's a big clue that the interior of the earth has a large liquid component to it. And indeed, we saw that the structure of the earth, we had the crust on the outside, we had the mantle underneath, and then we had the core. And that core had two parts. It had an outer part and an inner part. The outer core is liquid and the inner core is solid. And so if this is the earth and I have an earthquake and it's sending a sound wave through the earth, it can travel through the mantle, but when it gets to the core, that outer core is liquid, and so the P waves can keep going through, but the S waves will just stop. They'll be absorbed by that liquid material. So what Oldham had discovered was the boundary between the solid mantle and the liquid outer core, the core-mantle boundary. So in 1909, and I apologize, I don't know how to pronounce this name properly. I think it's something like Andrija Mohorovic. That's probably not right. But anyway, this person here, they observed a sharp increase in the seismic velocity at a shallow layer within the Earth. And basically, he had discovered the boundary between the crust and the mantle. And so the Earth is composed of a thin outer crust that sits on top of a layer of denser material, i.e. the mantle. Now, in 1913, Benno Gutenberg refined Odom's work by locating the depth of the core mantle boundary. He found that it was about 2,900 kilometers deep. And basically, when P waves reach this depth, they refract so strongly that the boundary casts a P wave shadow where no other waves are detected over part of the Earth. And so you can see that in this figure here. As you can see, so imagine you have an earthquake happening right here. Now this is a region where you have the mantle, where both P waves and S waves can occur. Now you can see they're kind of bending around. That's because they're going through different layers of material, and that causes them to bend. But when they reach the boundary with the core, they really bend a lot because they've gone to a very different kind of material. Remember that outer core is liquid. And so you get... So these guys are bending in kind of a regular way, and then they hit that core and they really bend. And so that creates what's called a shadow zone, where there's basically, if you had a seismograph here, you wouldn't detect any waves at all because they're in that shadow zone. But then you get back over here, and what you find is the P waves have traveled through the core, but the S waves have stopped. And so that's how we know that there's a liquid component to this core, because P waves can go through a liquid, but S waves can't. And then for some of the waves, they actually go through the inner core, which is another radical density change that causes a lot of bending, and that really makes everything go kind of wonky. But geologists have been able to figure out by having an earthquake happen here and have seismographs all around the world and figuring out, okay, this happened at this time and this earthquake reached over here at this time and this was detected at this time later and these were found at different times later. They've been able to deduce all of this structure, the crust, the mantle, the outer core, and the inner core, just by examining the sound waves passing through the Earth, which is a pretty impressive feat if you think about it. So let's examine the core in a little bit more detail and some things that we know about. First of all, we know that the core is composed predominantly of metallic iron. We know that because we've been able to figure out what the velocity of the sound wave is passing through those regions, and we know that it's the velocity that sound travels through iron. Now, the core has two layers, the solid inner core and the liquid outer core. The inner core is solid because of the pressure. Think of like if you go swimming in the ocean, the deeper you go, the more pressure you feel. It's the same in the Earth, and so the deeper you are in the Earth towards the center, the greater the pressure you'll feel. So that's why the outer core is able to remain liquid and able to flow in a liquid phase. And flow in the outer core produces the Earth's magnetic field, which you've heard about, of course. You know that, for example, a compass works because the compass is basically a magnet that interacts with the Earth's magnetic field. Anyway, that's generated in the outer core. Now we can look at the structure of the different layers. The mantle makes up 82% of the Earth's volume and 65% of the Earth's mass. So the mantle is by far the largest part of the Earth's structure, and it's also the thickest layer, about 2,900 kilometers from top to bottom. The mantle rock is rich in silicon and oxygen. It also contains heavier elements like iron, magnesium, calcium, but primarily it's compounds of silicon and oxygen. Now, the mantle is actually divided into two regions, the upper mantle and the lower mantle. And then the upper mantle is actually subdivided into two additional zones, the asthenosphere and the lithosphere. The lower part of the upper mantle is called the asthenosphere, and the asthenosphere is solid but behaves in a plastic-like manner, allowing it to flow easily. Now, when most people think of plastic, they think of petroleum-based plastics, like, the kind of container that your Coca-Cola might come in, but it's not exactly the same kind of a thing. Think of a material like silly putty. If you've ever played with silly putty, you know that it's very malleable and squishy, and it can actually flow. So if I put a wad of silly putty on a piece of wood and I tilt that wood up at a pretty steep angle, that silly putty will actually creep down the incline of that block of wood. And so gravity will sort of stretch it out and pull it down the inclined plane. It'll flow almost like a liquid. But at the same time, if I ball that silly putty up into a ball and I throw it at the floor really hard, it'll bounce like a solid. And so silly putty is kind of a material that can, depending on the conditions it's subjected to, it can either flow like a liquid or it can react like a solid. And it's the same kind of idea in the asthenosphere. It behaves in this kind of material where it's a solid material, but it also can kind of flow like a liquid. And this flowing motion of the asthenosphere actually affects the surface features of the crust. Now, the lithosphere includes the uppermost part of the upper mantle plus the crust. And the lithosphere is cool and rigid. It does not flow, but it rides atop the plastically flowing asthenosphere. Because of its brittle nature, the lithosphere is broken up into individual plates. And movement of these lithospheric plates cause earthquakes, volcanic activity, and deformation of rock. Now, the lower mantle extends from a depth of about 700 kilometers down to the outer core, and the lower mantle is under great pressure, making it solid. The next layer we want to look at is the Earth's crust. Now, the Earth's crust has two distinct regions. There seems to be a lot of that going around in this presentation. Lots of things have two distinct regions, but that's okay. What are the two distinct regions of the Earth's crust? There is the oceanic crust, which is composed of dense basaltic rocks, and it's very compact, it's thin, its average thickness is about 10 kilometers. And so that's the part of the Earth's crust right underneath the ocean. And so you see here's the mantle, here's the ocean, and between the mantle and the ocean is the thin layer of crust that's about 10 kilometers wide. Now, under the land masses, we have the continental crust. And that's composed of less dense granite rocks, and that tends to go around 20 to 60 kilometers. So we can see under the land masses, the crust extends way deeper. And so here we have basaltic rock material, here we have granite. So different type of material and also different sizes. Now the next thing we want to talk about is the theory of continental drift. An idea before its time. When it was first proposed, nobody really believed it. It was kind of almost a joke to people, but it turned out that it was right. And it was proposed by a guy named Alfred Wegener, and his hypothesis was this: the world's continents are in motion and have been drifting apart into different configurations over geological time. If you look at a globe of the Earth and you look at Africa and you look at South America, it's very clear that South America, if you were to tilt it and scoot it over, it would fit almost perfectly wedged underneath Africa. And so he saw this, and he saw things like this, and it seemed to him that maybe that these continents long, long ago had been joined together and over time had drifted apart. And that's exactly what had happened. The different continents are drifting away from one another, and that is the theory of continental drift. Now, at the time when all the continents were joined together, they formed a supercontinent which he named Pangaea, and that stands for Universal Land. Now, if you look at this picture here, you can see exactly what I was talking about, how South America seems to sort of fit alongside Africa, and the other continents kind of merge together as well. They fit together pretty well. And so this is what gave Wegener the idea that these continents, had once been joined together. But that wasn't just his idea. He went and looked for evidence to support his hypothesis. And he found not only in sort of the configuration how they all seem to fit together like a jigsaw puzzle, but he looked at fossil evidence, he looked at matching rock types, he looked at structural similarities in mountain chains on different continents, he looked at paleoclimatic evidence. So all these different lines of evidence supported his idea, and we now accept it as the truth about what happened on the Earth's history. So why didn't people accept his ideas even though he had a lot of evidence to suggest that they were correct? Well, he couldn't explain the how. He proposed the idea that the continents moved, and he provided evidence that they had moved, but he couldn't explain how they would move. How could you move something as big as a continent? And so without being able to explain it, people just didn't buy it, not for a long time. Now, if you look at detailed mappings of the seafloor, you find huge mountain ranges in the middle of ocean basins, and you also find deep trenches alongside some continental margins. So this tells us that the deepest parts of the ocean are near the continents, and out in the middle of the ocean, the water is relatively shallow. And so Harry Hess is the one who came up with the hypothesis to explain how continental drift worked. His basic idea was that the seafloor was spreading, and that provided the mechanism for continental drift. In other words, the seafloor is not permanent, it's constantly being renewed, and mid-ocean ridges are sites of new lithosphere formation. Oceanic trenches are sites of lithosphere destruction. And so you can see in the mantle there are these sort of currents that are convection currents that are pushing sort of the mantle up here and causing separation there. And that is what is causing the forces that are driving the continental drift. And so it turns out this seafloor spreading is supported by magnetic studies of the ocean floor. So basically what happens is lava is erupted at mid-ocean ridges, and that lava is rich in iron. And when the lava cools down, the iron basically it becomes magnetized. And the magnetite crystals in the iron, they line themselves up with the Earth's magnetic field, just like a compass needle. And one of the things that has come out of these studies is we've learned that the Earth's magnetic field, the poles, the North Pole and the South Pole, they actually flip. In other words, the North Pole turns into the South Pole and vice versa. This is known as magnetic reversal. So the seafloor spreading is supported, this theory of seafloor spreading is supported by the magnetic studies of the ocean floor. The seafloor holds a record of the Earth's magnetic field at the time the rocks of the seafloor cooled, because, as I said previously, they line up, the structure in the crystals of the rocks line up with the Earth's magnetic field. And this magnetic record appears as parallel zebra-like stripes on both sides of the mid-ocean ridges. And so the age of the ocean floor and the rate of seafloor spreading could be determined by measuring the magnetic fields produced in these ridges. And so with all the support for the theory of continental drift and an explanation for what causes it, it's a pretty well-established and well-accepted theory now. And that's the end of this lecture. We'll continue with the next lecture which will be available shortly.